Hi, welcome to the course on polynomials and the theory of equations. So this is the new course that I had promised when we hit the number of subscribers as 500. And I'm going to start this today. And hopefully you'll learn a lot in this course. The overview of the course basically is understanding polynomials, uh, properties of polynomials, questions that come related to this topic in Olympiads. So we'll do a lot of work on polynomials and theorems that are valid here. Connections of polynomials to number theory will be explored here. So this part we will cover. Then we'll go on to the theory of equations, which is basically how to solve location of roots, finding roots, finding roots for equations, and solving higher degree equations, solving higher degree, third degree, fourth degree equations. And eventually what I want to get to is a little bit of abstract algebra, like group theory, which is essential to understand how advanced maths is built towards this, and eventually getting into the proof of why a fifth degree equation has no roots in radicals. So this part is a little advanced. It depends on whether we have time and whether students are interested in this. But these topics are definitely something that we'll be doing. And these are very important from the perspective of both your Olympiads as well as from a perspective of JEE. So this is the brief overview of the course. And with that, I will just begin. And this video is all about basically what is a polynomial, and some properties, some nice properties and theorems about polynomials. So let's just begin. So I'm sure all of you are aware of a polynomial definition, but I'm also sure that you have not paid close attention to when you can call something a polynomial and when you cannot. So I'll just write down the definition here and then we'll work through some examples. So a function of a single variable, t is a polynomial, on its domain. So basically basically means when that function is defined. So a function of a variable t will be called a polynomial in its domain if we can put it in the form this is the form of a polynomial an t power n plus an minus 1 t power n minus 1 and so on till a1t plus a naught, where an minus 1 till a1 a naught belong to either real numbers or complex numbers. Basically they are constants. They could be either real numbers or complex numbers even, right? So what does this definition really mean? So what it means is a function of a single variable t, any function can be called a polynomial in its domain wherever it is defined if we can put it in this form, where it is written as a sum of monomials. Monomials means single terms which have an t power n. There is a constant and a t power n, where n is an integer, by the way. N is an integer. N is supposed to be an integer here. So let's look at some examples and try to understand what are polynomials. So examples of polynomials could be something like this: 3t cube minus 7t square plus 4t plus 1. This is a polynomial because you are expressing it in terms of f of t, where it is written as ai t power something, right? So 3t power 3, 7t power square, and so on, right? And this is also a polynomial: 8t power 6 minus t power 5 plus root 2t square plus root of minus 1 t minus 1. Now, this is also a polynomial, even though there is a weird term here that is root minus 1. And root minus 1 is generally denoted by I, and that is just a basic complex number. However, this is still a constant. So the definition wants you to ensure that all the an terms are constants, right? And this is also a constant, and the powers of t are integers. So this is a polynomial. What about this one? T square minus 1 by t minus 1. Is this a polynomial? If t is not equal to 1, yes, it is. It is just hidden, but you can factorize it and it can be written as t plus 1. So this is just disguised polynomial. Since t is not equal to 1, therefore this function is always defined, and it is actually in the form of t plus 1, which is a polynomial. What about this thing? Cos of, is f of t equal to cos of 2 cos inverse t? Is this a polynomial for minus 1 is less than equal to t is less than equal to 1? So on first glance, it looks like this will not be a polynomial, right? Because it doesn't even look remotely close to any function of t like this, right? A n t power n plus a n minus 1 t power n minus 1 and so on. It doesn't even look remotely close to this. However, actually, this is a polynomial because our definition said that the thing should be written in this form in its domain. So first of all, we have to check whether this function is defined or not. So anybody who has done a little bit of trigonometry will be able to follow this. We know that cos t has values between minus 1 to 1. Therefore, cos, the output of a cos is minus 1 to 1. So when I write cos inverse t, basically I am trying to tell you that this is the angle theta whose cosine cos theta is equal to t, right? So cos inverse t basically talks about what is the angle whose cos theta is equal to t, right? It is asking the inverse question here. So because cos theta will always be between minus 1 to 1, right? Therefore, if I say cos theta is equal to t, therefore t should be between minus 1 to 1. T should be between minus 1 to 1 here always, right? Because then only you cannot do cos inverse of 2 basically, right? Why can't you do cos inverse of 2? Because there is no angle theta whose cos theta can be 2. Because we know that cos theta value is always going to be between minus 1 and 1. So the reason this condition is given here is because the domain or the definition, when is cos inverse t defined? Cos inverse t is defined only when t is from minus 1 to 1. So that is something that you need to be aware of. However, we have still not answered our initial question. Is this a polynomial, right? So how do we think about it? Let's do it on the next page. So this is f of t is equal to cos of 2 cos inverse t, right? And minus 1 is less than t is less than equal to 1. Now think of cos inverse t as equal to some angle theta, right? So if cos inverse t is equal to some angle theta, then 2 cos inverse t is equal to 2 theta, right? So basically cos of 2 cos inverse t will be equal to cos of 2 theta, right? And if you know a little bit of basic trigonometric identities, cos 2 theta can be written as 2 cos square theta minus 1, right? 2 cos square theta minus 1, because this will become basically cos square theta minus sine square theta. So I'm just writing it in this way, 2 cos square theta minus 1. So what we get is that cos of 2 cos inverse t, 2 cos inverse t can be written like this. And if it can be written like this, then using this assumption, we can say that since cos inverse t is theta, t is equal to cos theta. So instead of here cos theta, I can put 2 t square minus 1, right? So actually, this function is just a disguised way of saying 2t square minus 1 for minus 1 is less than t is less than 1, right? So this is clearly a polynomial. 2t square minus 1, nobody has any doubts about that. That is definitely a polynomial. So Even though sometimes functions don't look like polynomials, they could be polynomials. However, an example where it is not a polynomial is t power 1 by 3. This is not a polynomial because the powers have to be integers, and here you have a fractional power, right? Also, sine t is not a polynomial. Sine t is not a polynomial because directly here there is no way to express it as a sum of powers with integer coefficients, right now. So I hope that is a little clear. What we will do is we will go a little deeper here and do a few more examples of polynomials. But before we do that, I want to tell you about some of the terms that are associated with polynomials, some nomenclature basically. So I want to understand leading coefficient, leading term, constant coefficient, constant coefficient, basically linear coefficient and linear term, monic polynomial, monic polynomial, degree of a polynomial. These terms we want to understand. Okay, so I will just write the general definition of a polynomial here. We have an t power n plus an minus 1 t power n minus 1 and so on till a1 t plus a naught, where an minus 1, a1, a naught are all constants, and this is my definition of a polynomial. So I'll just label what is the meaning of leading coefficient. Leading coefficient is basically an. Leading term will be your an t power n. Constant coefficient is obviously a naught. Linear coefficient is a1 because this term is the linear term which has degree 1. Linear term is a1t. Monic polynomial. If an is equal to 1, then the polynomial is monic. Then the polynomial is monic. So basically, monic polynomial means that the leading coefficient of that polynomial is equal to 1, right? What is degree of a polynomial? Degree is the n value, which is the power or exponent of the highest degree term. Highest degree term. So n here is the highest power, so that is called the degree of the polynomial. If you have a constant polynomial, right? So suppose somebody says function of t is such that it is equal to 5. Now this has no term involving t, no term involving t. So the degree of this polynomial is actually said to be 0. Degree is equal to 0 here because it is 5 into t power 0 actually, right? Now what about f of t? Suppose you have 0. If f of t is 0, then this is a 0 polynomial, and by convention it is defined that the degree of the 0 polynomial is minus infinity. Minus infinity. The reason we do that is just a purely conventional thing. So t power in minus infinity will tend to 0 basically, you're saying. And don't worry about this so much. Just know that if it is a 0 polynomial, by convention the degree is called minus infinity. And if it is a constant polynomial, the degree of that polynomial is called 0. And constant has to be other than 0, right? So with these terms that we are now aware of, we can now go through some examples and see if we can identify polynomials or not, right? So let's do that. So what I will do is I will list out some functions and you have to tell me whether they are polynomials or not. Actually, I will only tell you, but I'm just listing it out for the purpose of explanation. So let's look at these functions. T plus 1 by t, then 8t square plus t power 3 by 4 plus 2t 3 power by 2 minus 3t 9 by 4 plus 8. So out of these 6, you can say this is a polynomial, this is a polynomial, this is a polynomial, this is a polynomial. This is not a polynomial because t power minus 1 is there. You have to have positive integers here, right? This is not a polynomial, and this is not a polynomial because the powers are fractions here. Powers are fractions here. So these six were fairly easy. Now let's think about these. Seventh one is sine of 2 sine inverse t. So -1 is less than t is less than equal to 1. So this is the same type of problem that we saw earlier. So I want to think whether there is a tricky way in which it can become a function of t, right? And a polynomial function of t. So I will go forward in the same way. I will say sine inverse t is, let's say, theta. So 2 sine inverse t is equal to 2 theta. So sine of 2 sine inverse t is basically equal to sine 2 theta. And if you know your trigonometric identities, sine 2 theta is equal to 2 sine theta cos theta. So I'm getting sine of 2 sine inverse t is equal to 2 sine theta cos theta. This can be written as 2 sine theta root over 1 minus sine square theta. And now since sine theta was equal to t here, because t is equal to sine theta here, what we get is this is equal to 2t root over 1 minus t square. Now clearly this function is becoming 2t root over 1 minus t square. So it is not, you cannot express it without removing the root, and it is not coming in the proper form for a basic polynomial. So this is not a polynomial. This is not a polynomial. So this is also cross. However, cos 2 cos inverse 2 t, we saw that it was a polynomial, right? So sometimes you have to be a little careful. You have to be able to understand these things. So think about, is sine of 3 sine inverse t going to be a polynomial? Uh, it's the same logic again. Let's think about it. If sine inverse t is equal to theta, then t is equal to sine theta we have, and 3 sine inverse t is basically 3 theta. So sine of 3 sine inverse t will be equal to sine 3 theta. And I know an identity that sine 3 theta is 3 sine theta minus 4 sine cube theta. So this is basically 3t minus 4t cube. So this is actually just 3t minus 4t cube. So it is clearly a polynomial. So I hope you have understood this inverse functions and trigonometric ways of expressing polynomials. And we'll now continue further with some more examples. Uh, is 2 power t a polynomial? No, 2 power t is not a polynomial. Log t, for example, is not a polynomial. T power half is not a polynomial. 1 plus t squared to the power minus 1, not a polynomial. So I hope you get the point basically. Anything that doesn't fit this pattern is not a polynomial, and sometimes the pattern could be hidden. So you have to explore whether actually you can write the function like this or not, right? So once this is clear, what we look at is some operations on polynomials. Operations on polynomials, you might be already aware of how to add and subtract two polynomials. So once you add and subtract two polynomials, you get a polynomial. So basically what you can say is polynomials, the set of polynomials is closed under addition and subtraction. What do we mean by set of polynomials is closed under that? So if you have p and q belonging to the set of polynomials, you can prove that p plus q will also belong to the set S, belongs to S also, and p minus q will also belong to the same set. So once you have a set of polynomials, all additions, subtractions of any combination of them will still lie in the same set. So that is something that is important to know. Multiplication of polynomials, I'm sure everyone is aware of. You just multiply term by term. Uh, so basically, if you have a n t power n plus a n minus 1 t power n minus 1 and so on till a1 t plus a naught, and I have to multiply this with bn t power n plus so on so on. So I will just multiply term by term. I'll get a n b n t power 2n and t power, you will get an minus 1 bn plus an minus 2 bn minus, no, an minus 2 into, no, this is fine. You also get an into bn minus 1 t power 2n minus 1, right? So t power 2n minus 1 can only come from these coefficients, because an will give t power n, and this will give t power n minus 1, and this will give t power n, and this will give t power n minus 1. So on. You can keep multiplying. It's just term by term multiplication. However, what I will tell you is a nice trick to multiply polynomials fast, and that is something that you might not be aware of. So let's look at this method, and this is called the method of detached coefficients. It's a very nice method because it helps you calculate polynomial multiplication very quickly. Method of detached coefficients. So let's see how to multiply. So for example, suppose you have to multiply tq plus 3t square minus 2t plus 4, and you have to multiply this with 2t square plus t plus 6, right? Suppose you have to multiply these two polynomials. I know everyone is aware of how to multiply in a normal manner. So you just take t cube, multiply with this, then t cube with this, then t cube with this, and so on, right? So now this method that we'll see is just that, exactly that, but done in a faster way where you don't worry about the power so much. You can get the answer really quickly. So what we'll do is we'll write all the terms here, and we'll not write the t parts, we'll write only the coefficients. So we'll write 1 plus 3 minus 2 plus 4, right? So I have written all the terms with the coefficients 1 plus 3 minus 2 plus 4. If there is some missing term here, I would have put a 0 in it, right? Then the next step is write the terms of this polynomial, write it like this, straight below the above polynomial from the left hand side, right? So I will write 2 plus 1 plus 6 in this case, right? Okay, so this is my first step. So once you have written all of these coefficients without the t powers, just start multiplying from this side, and just multiply every term 2 into 1, 2 into 3, 2 into minus 2, 2 into 4. So what I will write here is 2 into 1 is 2, 2 into 3 is 6, 2 into minus 2 is minus 4, 2 into 4 is 8, right? Okay, great. I have just multiplied 2 with all of those terms. Notice that actually what you're doing here is simply multiplying 2t square with everything here. There is nothing special about what we are doing. It's the same thing. But once you get a little used to this, this is super fast. Now, the second step, I'm multiplying 1 with all of these terms, okay? And now I will write 1 with a slight shift. So I will write 1 into 1, not here. I will write it here. 1 into 1, 1 into 3, 1 into minus 2, and 1 into 4. Then I will write 6 into 1, 6 into 3, 6 into minus 2, and 6 into 4. But I'll again shift it one step this side. 6 into 1 is 6, 6 into 3 is 18, 6 into minus 2 is minus 12, and 6 into 4 is 24. I will just rub off these arrows so that it is clear what we are doing. So now, what have I done? Basically, I multiplied 2 into 1, 2 into 3, 2 into minus 2, 2 into 4, then 1 into 1, 1 into 3, 1 into minus 2, 1 into 4, and I have shifted the things one step to the right, right? And then just add vertically, okay? Add vertically. So this is 2, this is 7, this is 6 minus 4, 2 plus 3, 5. This is 8 minus 2, 6 plus 8, 24. This is minus 8, and this is 24, right? And this is going to be your answer, and you fill in the powers of t now from this side. From this side, I'll fill in the powers of t. The first term will have 0 power, this term will have t power 1, this term will have t power 2, this term will have t power 3, this term will have t power 4, and this term will have t power 5. So this is my answer. Okay, actually it's just basic multiplication, but you will see if you use this method, you will see that it speeds up your calculations by a lot. Okay, so this will be the answer: 2t power 5 plus 74 plus 5t3 plus 24t square minus 8t1 plus 24. To convince you that this is useful, I will also show you another example. So let's say you have to multiply these polynomials, right? 4 2q plus 2t square plus 7t plus 1, and I will multiply this with 2t square plus t plus 6. Now you can try it with your method. I will try it with my method, and you can check, compare speeds. So you can say 8, 4, 14, 2, 4, 2, 7, 1, 24, 12, 42, 6. I will add 8, 8, 40, 31, no, not 31, 21, 43, 6. My answer is x square, x cube, x4, x5. So this is my answer, and I'm sure I am faster than the regular method. So if you do it by the regular method, you'll not get the answer so fast. So this method of detached coefficients is super useful. You should use it because it's quickens the pace, and you will need it in a competitive exam where there are multiple choice questions, and now suppose you have to multiply polynomials, you need to save time. So get used to this. Also, I can confirm and I can do some cheap tricks here. So for example, I'll show you, find out the value of 4271 into 216, right? I don't need to use a calculator to find this value, because now what I will do is, if I have to do this calculation, I will write it as a polynomial, and 4271 will be represented like a polynomial 4t cube plus 2t square plus 7t plus 1, and this will be written as 2t square plus t plus 6. And at a later stage, or at even this stage, I can say that if I put t is equal to 10 in this value will be 4271. No, obviously this is just the units, this is just the expansion of this number, right? And if you put t is equal to 10, this will become 4271. If you put t is equal to 10, this will become 4271 as well, right? This will become 216 as well, right? So instead of multiplying these two numbers, I'll multiply these two polynomials and put t is equal to 10 at the end, right? So this multiplication is basically by method of detached coefficients. I can do it really fast here. And at this step, I can say put the value of 10 here. So I'll get 8 into 10 power 5 plus 8 into 10 power 4 plus 40 into 10 power cube plus 21 into 100 plus 430 plus 6, right? So this is basically 2100 plus 436, so 2536, and this is 40,000, and this is 80,000, right? This is 80,000, and this is 800,000, right? 800,000 plus 80,000 plus 40,000, so 920,000 here, and plus 2536, right? So it is 922,536, right? Although you could have multiplied it as well, but I'm just showing you how you can actually fasten multiplication, or quicken the pace of your multiplication very easily. So this could be even more useful if the numbers were very big, 2, 5, 3, 7, 8, 9 multiplied by 1, 2, 3, right? Suppose you have something like this, right? So I can think of this as a polynomial in T and think of this as a polynomial in T, and do the method of detached coefficients, and at the end put T is equal to 10, right? So you should understand what is happening here. You could also do it like basically 253 T cube plus 789, right? And T cube is 10. T is equal to 10. This polynomial multiplied by this polynomial, 123 is a constant, right? There are multiple ways to do it. This polynomial into this polynomial also you could multiply by method of detached, but this has too many multiplications. So I prefer the normal way of writing it as 2, 5, 3, 7, 8, 9, 1, 2, 3. Do method of detached coefficients, get the terms in the final answer, and then put t is equal to 10 at the end, right? So that is just a side diversion. I just wanted to show you the method of detached coefficients, and basically facilitate a little bit of a faster multiplication of polynomials for you. Now at the end, what I want you to do is, what I want to discuss now is four theorems on polynomial, and we'll end the class with that. And these are very important theorems, so you need to be aware of these. Let's discuss these. So the first thing is, if A and B are two polynomials, if A and B are two polynomials, then degree of a plus b, degree of a plus minus b will always be less than equal to maximum of degree of a comma degree of b. And equality happens here. Degree of a plus minus b is equal to maxima if degree of a is not equal to degree of b. This is a very straightforward thing. You can think about it. If you take two polynomials, one is degree 2, one is degree 3. If you add it, it will be the degree of the resulting polynomial will be 3 only, right? Which is the maximum of degree of 2 and 3. So that is a straightforward theorem. The second part of this theorem is degree of a into b, product of two polynomials, will be equal to degree of a plus degree of b. So when you multiply two polynomials, the degrees get added. This is the first theorem. The second theorem that I want to talk about is given polynomials a and b, a and b not equal to 0, there are a and b not equal to 0, there are unique polynomials q and r, where q is called the quotient and r is called the residue, such that you can always write it, a can always be written as b into q plus r. A is written as b into q plus r, where degree of r, since it is a residue or a remainder, degree of r is less than degree of b. So this is exactly same as the Euclid's division algorithm or division lemma that you would have seen in basic number theory. So polynomials also can be divided, and when you divide, you get a quotient polynomial and a remainder polynomial or residue polynomial, such that degree of the residue will always be less than the degree of the b polynomial, right? And degree of the b polynomial, correct. So this is the second theorem. The third thing that we want to talk about is Bizot's theorem. Bizot's theorem says, which you probably might have heard as factor theorem, the polynomial p of x is divisible by x minus a if p of a is equal to 0. So this is something that is familiar to everyone. And the last thing that I want to discuss is if a polynomial p is divisible by a polynomial q, correct? Then every root of q is a root of p. Every root of q is a root of p. So what do we mean by root of a polynomial? A root of a polynomial is the value, any constant value that makes the polynomial equal to 0. So basically it's the solution of the equation p of x is 0. So if you have p of x is equal to 0 has some root alpha, and let's say p of q is equal to 0 has some root beta, and we know that q is a polynomial that divides p. Actually I made a mistake here. I'm saying q, so I should say q of x is equal to 0 at beta. So, and we know that p is a multiple of q, then obviously whenever q is 0, that is at beta, p will also become 0 because q is a factor of p. So q is inside p if you think about it. So whenever q becomes 0, p will also become 0. So this theorem seems very straightforward, but it has some nice applications. So if a polynomial p is divisible by a polynomial q, then every root of q is a root of p. So I will just end the class right now with these four theorems. In the next class, we'll take off from this point and we'll discuss a lot more of the properties of polynomials, and we'll get into the solving of equations. There are a lot of problems and difficult concepts that are coming here in this course, and these will be useful for slightly higher level Olympiads like INMO and IMO and all. So stay tuned, and I'll bring you great content in the next few videos for this series. I hope you understood something from this video, and please don't forget about that method of detached coefficients. Try it yourself. You will definitely feel the power of that method. It is faster than regular multiplication methods. So I hope you like the video. I'll see you next time.